Machado. He will tell us about approximate lattices and Ulam stabilities.
Thank you. Okay, so let's start with the first talk of today. Thank you very much to the organizers. One of them is arriving right now. Yeah, thank you for the invitation, the opportunity to speak here. So yeah, my talk today will be about this, approximate lattices, and their relation with Ulam stability or uniform stability. So it's a bit different from, I'd say, the talks we've seen so far. The idea will be that I will give a, say, hopefully gentle introduction to approximate lattices, explain a bit what they are, maybe present a few of the results that were obtained about their structure and all of that. So all of this is from, I'd say, a couple of years ago, something like that. And then in the second part of the talk, I'll try to open up a bit and explain how they are related to Ulam stability, and in a way how they can provide maybe a new perspective on Ulam stability. Okay, so there won't be results about Ulam stability per se, but there's just maybe other way to look at it. Okay, so I guess the first thing to do is really to define approximate lattices. I will redefine Ulam stability as well, but I'm pretty sure members of the audience are more familiar with that. So let's talk about approximate lattices. So the approximate lattices are a generalization of lattices in locally compact groups. Okay, so the definition is as follows. So if you take G, a locally compact group, you will say that a subset, usually called lambda of G, is an approximate lattice if, well, we'll have to satisfy three conditions. So lattices are subgroups that are discrete and have finite covolume. So what we'll generalize is the subgroup part. But let's start with the easier one. So first of all, I want my subset to be discrete in a nice way. So let's say uniformly discrete, which means that I can write that as, well, if you imagine that you have a nice distance, the distance between the 2 points of lambda is at least some constant. So if I take 2 points, okay, the distance, the infimum over all the pairs is at least some 0. Okay, where here I'm imagining that D is some compatible left invariant distance on G. Okay. So okay, maybe here I'm restricting the case a bit, but yeah, that's just a good way to look at it. The second part is, well, finite covolume. And finite covolume here, we're going to take maybe the easiest way to define it. It's simply that there exists some set F in G, okay, with finite Haar measure such that, well, lambda times F, which is simply the set of all products of one element of lambda and one element of F. Okay, so it's the lambda F. This is equal to the whole group. Okay, so you have a sort of fundamental domain. It's not quite a fundamental domain, but yeah, it's nice enough. Again, the third part. So far, it looks a lot like the definition of lattices. The third part is going to be where the generalization happens, and it's the third part, which is lambda is an approximate subgroup. So now I have to define approximate subgroups. I haven't said much. Okay. So the idea behind these approximate subgroups is that they are subsets of groups that look a lot like subgroups in the sense that they are almost or approximately closed under multiplication. Okay, and so how do you define that? So first, you will assume that that lambda is symmetric. So the identity is in lambda, and lambda contains is equal to lambda 1, so it contains the inverse of every element that is in it. That's a good assumption. And the last and maybe the most important assumption is that there exists F, a subset in G that is finite, such that when I take the square of lambda, and here by that I mean the set of products of two elements, this is contained in F times lambda, or here again, the F times lambda. Okay? So you can read that as up to a finite error that is controlled by this set F, lambda is closed under multiplication. Okay, so when you might have a rather large set, but when you take successive products, you don't actually escape this set too much. Or at least you escape it, but in a way that you can control algebraically with F. Okay, so that's the definition of an approximate lattice. Again, so maybe a good thing to do is to give you a few examples. Okay. So the first person who studied these objects is Yves Meyer in the 70s, and he studied it in relations with a series of objects in aperiodic order that are actually quite well known. So first introduced. Okay, so Yves Meyer focused on the case of G abelian. Okay, but the definition extends that way. So he studied them because they generalized at once a bunch of different objects. So obviously, approximate lattices, as I said, generalize lattices in locally compact groups. So this gives you good examples that are already very interesting. An example that is maybe sometimes a bit more surprising and interesting for the people who come from Oxford is the vertices of a Penrose tiling. So not all Penrose tilings, but some of them. So I think P3 at least. So if you work or study in Oxford, you probably walk on approximate lattices. You can find that. So maybe you've heard of the hat tiling. So a lot of tilings works as well with tilings in the family of the hat tilings. Let's say like the hat. So I'm not sure it works for the hat. I know it works for the spectre or something like that. So it's a whole family. Anyway, that's just to say that in a periodic order, and when you work with tilings, these things show up a lot. And an example that is going to be a bit more interesting to us today is the set of Piso-Salem numbers. So something coming from number theory. And a class of subsets that is easy to define and quite interesting. So the way I'm going to construct them, I'm going to choose in R a number field. Okay. In my mind, it's going to be Q or Q square root of 2 usually. So that's just examples. Okay, and then the set of piso-Salem numbers of k, which I will denote by pk, is equal to all these algebraic integers such that if I take a Galois conjugate, alpha prime, of alpha, then its modulus is smaller than 1. Okay, so that's a subset. And what I want to do, I want to add an extra condition here because I really want the piso numbers that are really related to k and not to some subfield. So we add the condition that the field generated by alpha is equal to k. Okay, so this is more of a convenience condition. It's nice. Okay, so slightly silly example. The piso numbers of Q are integers. The piso numbers of Q square root of 2 are all these A plus B square root of 2 with A and B integers such that A minus B square root of 2 is smaller than 1. Okay? And I have, and B is non-zero, I guess. Okay, so these are nice examples, and actually that gives you a whole family of approximate lattices in R. Okay, every single one of them. If you choose a number field, every single one of them is going to be an approximate lattice. Okay, so that's a very nice thing. It's perhaps slightly surprising that they are approximate subgroups when you think about them for the first time. It's not actually that difficult to show, but it's something slightly surprising. Another interesting thing to note about these piso numbers is that this set is stable under product. Okay? If you take the product of two piso numbers, this condition there is still satisfied. Okay? The Galois conjugates are just products of the Galois conjugates, and so you still get this condition. And the very nice thing about that is now we don't only have something that is an approximate subgroup; it's a sort of approximate subring. Okay, and what you can do as soon as you have rings is you can start making matrices out of them or groups of matrices. And what's that leading us to is the fact that we can create approximate lattices in groups of matrices using these piso numbers as coefficients. Yeah? So that's something that we can do. And that's maybe the last family of examples I give. So now you still have what you can define, for instance, is this set SLN of Pk. Okay, and this is simply a set of matrices in SLN of K. Okay, and you want to say that they have coefficients in Pk. It's not quite that. Yes, you say that the identity minus A and also the identity minus A inverse both have coefficients in Pk. Okay, and I write it like that. Okay. And there you have it. You've built a family of interesting approximate lattices in SLNR. Yeah.
Can you say what is the finite set F in the case of, say, Q square root 2? Is it easy to see?
Yeah, not really. Yeah.
So, is this alpha prime like not equal to alpha? Because if A plus
Oh yeah. Of course, it's like the sort of proper Galois conjugates. Yeah, the one's not equal to alpha. Yeah, you're right. Yeah, otherwise this would give you that the only element is 1. Yeah. Okay, so you've got a nice family and nice family of examples, and you can see that actually this is not specific to SLN. So you can, if you have any, if you have any group, linear group in GLN defined over K, you could do exactly the same construction. Provided that G doesn't factor through a multiplicative group, like by the Borel-Harris-Chandra theorem, you'll get an approximate lattice in the R points. Okay, so you get like that a very nice family of examples. One thing that was very interesting to Yves Meyer is that even though you had actually quite a lot of examples, and these things might be actually quite chaotic when you look at the points, he could find, in the case of abelian groups, a very nice classification of all approximate lattices. Okay, and so that was Meyer's theorem. And so he says if lambda I restrict to Rn, but he proved his theorem in abelian locally compact groups more generally. So if you have an approximate lattice, well then what you can do is there is a lattice gamma in a group that is higher dimensional. Okay, so in Rn times Rm, a lattice such that well, lambda is contained, and what we're writing that P of Rn Okay, so here what Meyer says is that actually these approximate lattices, which are objects that are very periodic, as the Penrose tiling example shows, they come from something that is extremely periodic and is actually a lattice in higher dimension. How do you get it from a lattice? Well, what you do is this procedure is called the cut-on project. So you imagine you have your grid of points, and it lives, let's say, in a higher dimensional space. So this is your, say, Rn. This is your Rm. And here you have a grid of points. What you do is you're going to select, to first cut a strip, select all the points in your grid that are sufficiently close to this horizontal line. Okay? And then you're going to project it to the Rn. So that is what this pi of Rn is the projection to the first coordinate. So it's the cut and project method. And you can see that, so one thing you can see easily is that this is still a discrete subset. Because if you were to take any window of this tube, here you get only finitely many points in it. Okay? So once you project, you get only finitely many points in any compact region. Showing that this is still finite covolume is slightly more annoying, and same for approximate groups, but it's still relatively elementary once you get into it. Okay, so this is the cut-on project method, and actually once you have that, well, you have an approximate lattice and something that is what we call model set, but that is also an approximate lattice. So there's a commensurability thing happening, which means that then you can find some finite set F such that you have that. So if you don't really care about the classification, if you only care about the classification up to this sort of finite modifications, then all the approximate lattices are obtained through this very regular method. Okay, so that was Meyer's idea, and the question was, does it work more generally? Okay, so what does that mean? You have to generalize this cut and project method. And it turns out that it's not really that difficult to generalize. So, cut and project. So there's really nothing that prevents me from defining cut and project more generally. So I take G and H, two locally compact groups. I take a lattice in G times H, okay? And instead of this very nice box, what I can do is just take a neighborhood of the identity, compact neighborhood of the identity in H, which we call the window. So compact or relatively compact is enough. Neighborhood of the identity in H, okay? And then define the model set as the projection to G of gamma intersected with the strip around G. Okay? And that's what you call a model set. So if I go back to my picture, so gamma is the grid, this is my G, and this is H, and this is the window W0. Okay?
Could you please push the lower?
Yeah. Is that enough or? Okay. So now that we have a general cut and project method, the obvious question is, given an approximate lattice in a general locally compact group, is it well commensurable, or is it related in a way? Is it a model set? Okay, is it constructed from this cut and project method? And so there's been quite a bit of work around that. So there's been quite a bit of work around that. So the first result I will mention is the fact that Meyer's result actually generalizes completely to the case of amenable groups. Okay, which is nice. Amenable groups are nice. If G is amenable, okay, and the way you do that is by borrowing ideas from multiplicative combinatorics or additive combinatorics, which usually deals with finite approximate subgroups. But here, because you are amenable, you have something that can measure also sizes. You have a sort of mean or finitely additive measure that lives on the space that you can define, and you can use that to do exactly the same tricks as in additive combinatorics, and that helps you do that. But what that method gives you on top is that you can actually locate a bit better where you find your model set, and this is something that will become very relevant later. We can choose that. So lambda is contained in M. This is the model set. So a set obtained through the cut and project construction. But M is not actually that far from lambda in the sense that I don't have to take that many products of lambda to find M. It's in lambda to the 8. Yeah.
And is H amenable?
Yeah. Yeah, you can okay. Like that, I'm not sure you can take H amenable. You can take H amenable, but you have to do a few modifications to lambda. It's not going to contain the whole of lambda, but just a, let's say, finite index subset of lambda. But yeah, you can. But this is much more difficult. This is not given straight away from the result. Okay. Okay, but that's something very nice that you can actually locate or say that M is actually very close to lambda. Yeah. Okay. So that's a measure of that. This lambda to the 8. Complementary to that, Reshevsky came up. Proved that in semi-simple groups, the same thing happens. Okay, but he actually proved something slightly different and actually very interesting. If G is semi-simple, okay, and I have two comments about this result. So first, there is no analog to this. And that cannot be, actually. Okay. And you can say a bit more what is the approximate lattice we obtain, and actually, any approximate lattice let's say that is not a lattice is arithmetic. Okay, so I'm not going to define fully what arithmetic means here, but you get probably a good idea from that. Okay, so there is a slight generalization of the Piso numbers, and essentially your approximate lattice is going to be commensurable to something that is a G of pk. Okay, so that's a beautiful theorem. That in a sense generalizes Margolis' arithmeticity theorem.
Does it use Margolis' arithmeticity?
It does, yeah. And it doesn't reprove Margolis' arithmeticity theorem. That would be cool.
But you're saying an approximate lattice in SL2R, which is not a lattice, is arithmetic?
Yeah, that is the... Oh, thank you. You actually stole my remark. Perfect. Great effect. So yeah, exactly. That is the beautiful thing. I don't even have rank assumption. The way you can think about it is the fact that the group generated by my approximate lattice plays the role of the commensurator. Okay, and if this group is not discrete, if this group is discrete, then this group is a lattice, and essentially your approximate lattice is already a sort of lattice. If this group is not discrete, you have a dense commensurator, and there's this criterion of I mean, it's related to this criterion of Margulis that says that a lattice with dense commensurator is arithmetic. So it's not super surprising.
But is it really like, because when it's not an actual lattice, you need to add more factors and then it becomes high rank?
Yes. Yeah, exactly. It automatically becomes high rank. You have a sort of like hidden factor that is this H here. This hidden factor gives you higher rank automatically. Yeah.
So what do you mean? The answer is yes, but star doesn't hold?
That means that for all n greater than 0, I can find an approximate lattice such that there is no model set that is in between lambda and lambda to the n.
Question is about the 8, whether there is a uniform power.
Yeah, so the question becomes whether there's a uniform power. And here there's just no uniform power at all. There's no it's not like specifically about 8. Okay?
Just to make sure, when you say model set, it is the set that was cut after projection?
Exactly, yeah, that's this thing. This is the model set.
Okay.
Okay? And so now something interesting is that you know that it's true for all amenable groups, you know that it's true for all semi-simple groups, you know that a Lie group is always built out of an amenable and a semi-simple group, and you want really badly that the whole thing can be extended to just all Lie groups, and it turns out that it cannot, because otherwise it wouldn't be fun.
Did you say what an arithmetic approximate lattice is?
Yeah, so I didn't. All I said is that it's essentially this.
Okay.
It's a construction like this. It's a G of pk. So you can do something a bit more general than pk, but it's essentially G of the Piso numbers or something along those lines. Or you can think of it as a cut-and project where the lattice is arithmetic. Okay, so no, and actually you don't have to look for very complicated sets to find out that this fails. And this is again, Reshevsky's example is slightly more complicated than the one I'm describing, but this is a slight modification. No, already in maybe the simplest example of a mixed group, SL2R times R. As soon as you have a bit of both, this is not going to work. Okay, but and so the example is, I think, very instructive because the thing you're going to use is something related to bounded cohomology. Actually, you're going to use a quasimorphism, and you're going to use one that is not close to a homomorphism, and you'll see that this is going to create a lot of problems. So let's explain that because this is quite instructive. So how do I build an approximate lattice that is not in any way related to a model set? What I do is I first pick a lattice in SL2R, so I start very simply. So your favorite lattice could be co-compact or not. So yeah, gamma could be SL2Z, or the free group inside SL2, or a free group inside SL2Z. Okay, so this is a lattice in SL2R. What you want now is you want to take a quasimorphism. Okay, so I have two things already. I have a lattice in SL2R. I have a quasimorphism. And the other thing I will want is an approximate lattice in R. Okay, and I take one of these examples, so I will consider this approximate lattice. Okay, this is an approximate lattice in R. And now, well, if I'm just given this lattice and this approximate lattice, a good construction is that. Okay, this is a new approximate lattice. Inside SL2R times R. But it doesn't really bring anything new, and you can see that because gamma is a lattice and because this is a model set, this whole thing is a model set. So the thing you want to do is, well, I introduce this quasi-homomorphism, this quasi-morphism. Okay, and I will use it to sort of skew this this product. Okay? So maybe you can write it something like that. How do I do that? I need to prep things a little. I will add an assumption on F. And the assumption is that F of gamma minus 1 is equal to minus F of gamma. Okay, symmetry assumption. And also an assumption on the range of F. I will want it to be related to this thing. So all I'm going to say is that F of gamma is included in the square root of 2. Okay, because the square root of 2 is dense in R, this is not actually a big assumption. I can just take any quasi-morphism I like, modify it by a tiny amount, I get a quasi-morphism that takes values in this thing. Okay, so this is really not, this is more massaging my quasi-morphism rather than a big assumption. Okay, so now I can define, okay, so let's call it lambda f. Now I can define lambda f to be the set of gammas and x, okay, such that what do I want? I wanted this when I take the Galois conjugate is smaller than some big constant actually. Okay, and here, what do I mean by that? This lives in gamma times z square root of 2. Okay, and this is my notation for the Galois conjugate of x. Okay. And here you can see that if I choose f to be the trivial, the trivial quasimorphism, what I'm really defining again, so is the direct product of gamma and the piso lambdas up to some finite thing. Okay, so I'm just doing the same definition, but I'm skewing it using this quasi-homomorphism, and that's the definition. And there's something nice that happens is that you can, given f, you can check whether lambda of f is well commensurated to one of these model sets by looking at the bounded cohomology. Okay, so essentially, if f is within bounded distance of a homomorphism, this is a model set. And if F is not, this is never a model set. Okay? Also, in a rather strong way, lambda F and lambda F primes are all the same, or isomorphic, or commensurable, if and only if F and F prime are within bounded distance. Okay, so this gives you a very nice thing. And it turns out that the whole structure of approximate lattices goes like that. Okay, so let me state that. Maybe I'll use the other one. So we've seen an example that says that essentially the big question cannot be answered affirmatively all the time, but it turns out that you can still find a classification of all approximate lattices in great generality. So I'll state the theorem a little informally. So in the case where my group G is the R points of a linear algebraic group, maybe I write something like that. It's the semi-direct product of some semi-simple group with a solvable group. So I'm making a slight assumption here, but like it's not a necessary one, it's just for convenience. Then every approximate lattice in GR is built from three pieces of information. The first one is an approximate lattice, let's say lambda S in SR, an approximate lattice lambda R in the solvable part. So you have first an approximate lattice here, an approximate lattice here, and I'm just going to take an extension and a bounded cocycle to some mysterious space. Here the space is going to be, so in this case the space is R, but it's the R essentially that is seen as that is obtained in the R we see we'll see here is related to this H essentially. Okay. So the idea is that lambda S, because it's an amenable group, comes from a Cotton project construction. So there's a dual space essentially, and this V is related to this dual H. Okay, so it's mystery, but it's actually you can pinpoint it relatively easily. And so you have these two approximate lattices, this bounded cocycle, and well, your approximate lattice is going to be essentially something like. I write it like that. It's lambda S, an extension of lambda S by lambda R, and the way you create the product is by twisting it by some alpha. Okay, so that's a general thing. One thing you can say is if alpha is equal to, so if alpha in the bounded cohomology is equal to 0, okay, if this class is equal to 0, then this gives rise to a model set. Okay? So it's not quite an if and only if, because it turns out that this is not exactly the right notion of cohomology that you need. The correct cohomology is slightly different. It's not the bounded cohomology of the group generated by lambda s exactly, but it's the cohomology that's given by the cochains that are bounded on bounded on lambda s essentially. Okay, so bounded just on the approximate subgroup and not on the whole group. It's a sort of cohomology that lives in between the group cohomology and the bounded cohomology, and it's in that space that you have to check. And it turns out that all the theory of Berger mono and all of that extends to this cohomology. Yeah.
So is that what you mean by bounded cocycle there?
No, it's actually a bounded cocycle in the sense of bounded cohomology. But what you care about its image in this other cohomology group and whether it becomes 0 or not. Okay, so since I want to speak about Ulam stability at some point, I'm not going to go in that direction. But it's just to say that there's this other sort of intermediate cohomology theory that sits in between the group cohomology and the bounded cohomology, for which you can compute essentially the cohomology groups when you're in these situations. So when lambda s is an approximate lattice in a semi-simple group, you can compute in particular the comparison map with the usual cohomology, and it vanishes as soon as you higher rank, and it's infinite dimensional when you're rank 1 lattice. And yeah, so that gives you a full, very nice theory. Classification theory for approximate lattices.
Can I ask you about the twisted notation?
Yeah.
So this is correct, right? The second coordinate is in C adjoint square root 2. It's not in the Piso-Salem numbers.
Yeah, so it is. Yeah, exactly. This is correct. So you're sort of not taking them always in the Piso-Salem numbers. So if you didn't have that, then that essentially means that it's in the Piso-Salem numbers. If you didn't have that and you had 1 here, there you're just saying the second coordinate is in the Piso-Salem numbers. But what I'm saying is I don't want exactly the Piso-Salem numbers. I want something that is a shifted thing, and this shift is going to be given by the quasimorphism. And that is this quasimorphism is creating the difficulty, I'd say.
So the second coordinate somehow here would be like in this mysterious V?
Exactly. This mysterious V becomes so this is like, there's a play, a bit like in Fourier theory, between the physical space and the internal space. So in a Cotton project, G is the physical space essentially, and H is the internal space. And so yeah. Alpha lives, so V is something that lives in this internal space, and that's what you use. Okay, so there is this nice theory, but there's one thing that is interesting, is that in the amenable case, you get this very nice result that tells you where you can locate your model set in what you could say is a very concrete way. Okay, you don't have to. You could, in a sense, take M to be lambda to the 8. And as I said, in semi-simple groups and in this thing in general, you don't actually know how. So I'm saying that any approximate lattice is close to something like that. I don't know how close it is. They can be actually quite far. And that is a difficulty, but there's a sort of conjecture. That if lambda is an approximate lattice in, let's say, I restrict to SLNR, the conjecture holds for more general semi-simple groups of higher rank. Okay, if lambda is an approximate lattice in SLNR, there is a model set M that is such that lambda is contained in M, which is contained in lambda to the small m for some universal m. Again, this is a relatively natural question from the sort of point of view of multiplicative combinatorics. It's also related to definability questions from the point of view of Wojciechowski. So Wojciechowski's approach is very model theoretic. And so this is related to definability questions. And it turns out that this is also related to Ulam stability. Okay, and that's what I want to talk about. Okay. Okay. So maybe I'll say that again. So one nice thing with the approximate lattices and this construction of Meyer initially is that for some interesting reason they pop up very often in what can seem to be unrelated problems. You find these objects very often because they sit just right at they are quite structured additively or multiplicatively speaking, but you still have quite a lot of freedom in the sense that you can always remove a finite number of points, or you can make small modifications. So they produce a lot of interesting subsets with both a lot of structure and also a lot of flexibility. Okay, so this is why they appear very often. And one place where they appear in, I think, an interesting way is in Ulam stability. So the setup might be a little silly, but if you take gamma in some locally compact group, a lattice, and you choose epsilon greater than 0, and an epsilon representation, so some map, gamma, that goes from gamma to un for some n, okay? An epsilon rep, which means, I recall that, so if I take any gamma 1, gamma 2, and gamma, in the operator norm is smaller than epsilon. Okay, so that's, I'm given an epsilon rep. Then there's a very natural way to define an approximate lattice out of that. That might be a bit silly at first, but that's where you'll understand, slowly we'll see why this kind of things matter a lot. So the subset I want to define is lambda is equal to pi minus 1 of the ball around the identity of radius, I think, 10 epsilon. Okay? So this is the ball in UN with the operator norm. I take a small ball, but sufficiently large that the radius is a bit bigger than epsilon. I get this. Okay, maybe I need an assumption on the fact that pi is symmetric, but it can be done easily. And then this is a subset of gamma, so it's a subset of G, and this is an approximate lattice. Okay. So it's a slightly, from the point of view of commensurability, it's a slightly silly one, because you can see that actually, so perfect. You can see that there exists a finite subset in gamma, finite, such that gamma is actually equal to f times lambda. Okay, so this is a rather large approximate lattice in some lattice. But that doesn't mean it's not going to tell us anything interesting. Because there's one thing related to that and related to that. It's an observation. I think it's this one. That uses the point of view of, say, model theory or additive combinatorics. So here, lambda is still this lambda. If there is a model set M such that lambda contains M, and M is itself containing lambda to the M, or some small n, then alpha is within distance c. So it's a constant that depends only on M times epsilon of a representation. Okay, so if you can somehow show that you have something like that happening, then you know that actually your epsilon representation was already close in the sense depending to that, from an actual representation. So one corollary of that observation and of this is that amenable groups are Ulam stable. Okay, this is a very circumambulated proof, but it's different. It's a different proof. Okay. Okay. In a sense, for a finite dimension.
Is this also an approximate lattice when your approximate representation is into an infinite dimensional symmetry group?
No, it becomes different. So some of these observations still
Which
hold.
observation doesn't hold? Because this cannot.
It's not an approximate lattice anymore. So you can't really talk about model sets in that way. But there's still something that holds.
So you get a finite set from a compact covering of the image?
So here you get a finite set from the compactness. And in infinite dimension, you can't do that, and so that's a problem. So I have 30 seconds to do my final remark, so very well timed. The thing is, you don't actually need something as strong as amenable groups. What you need is existence of precisely one invariant measure somewhere, and this somewhere can be located. So given lambda, what you want to define is the invariant hull of lambda, which is simply equal to the closure of the orbit of one of the indicator function of lambda in 0, 1 to the gamma. Okay? And a lemma or proposition is that if omega lambda has a gamma invariant probability measure, then there is a model set M I think it's 16. So obviously so this space is compact, and when, oh, I'm over time. Anyway, so obviously when gamma is immutable, this space has an invariant measure, and you reprove this corollary again. But in many cases, like when gamma is a lattice in a higher rank group, it seems very likely that you can adapt ideas from the Nebo-Zimmer structure theory for these actions, or Margolis's proof of the normal subgroup theorem to prove existence of invariant probability measures. Maybe not on omega lambda, but on something slightly bigger. Okay, and that's the end of my talk.
So in all of these things, does the n from un not matter?
No. No, the n doesn't matter. The only thing that matters is that it's finite, and so my group is compact. Yeah.
Can you hint why the operator norm makes a difference versus take a different norm on the unitary group where in all of this it's mapped like?
So I haven't. So it's to get. Okay, so it matters essentially at the end of this observation when you say, oh, if I have something in lambda squished between lambda and lambda to the m, the approximation will depend only on a constant that depends on m times epsilon.
The fact that it's a constant depends on.
Yeah. Otherwise, I think if you had like another norm that maybe Hilbert-Schmidt or something like that, you'd have something that depends on the dimension with this construction. That would be my guess. So that's, I mean, the nice thing. I mean, I guess submultiplicative is enough. Operator norm in itself is maybe a bit overkilling it, but yeah.
So in your conjecture, does little m depend on little m, or little m really absolute?
I think it depends on little n. Yeah. In this conjecture there. So the idea is that the main thing is that most likely there's not going to be an invariant measure there. You will have to go slightly. You have to look at sets that are a bit bigger than that. This is a This is not quite big enough in general, because lambda can be a bit odd. But a usual thing in let's say in this kind of combinatorics is that if your initial set lambda is not regular enough, if you take sufficiently high powers, this becomes more and more regular. And there's good reasons to believe that this will allow you to get. So it's probably going to be omega of lambda to some m that is going to have an invariant measure, and not omega lambda itself. And so you can actually construct examples where this doesn't have an invariant measure, but every time you construct such an example, lambda squared still has an invariant measure.
We now have half break. So let us thank Simon again.